Have you ever heard of atomic force microscope? Let's go back to the beginning. Everything started in the 17th century, when Robert Hooke invented a machine using lenses which overcome the human eye's capacity, the optical microscope. In 1923, Louis-Victor de Broglie created a new theory, the wave-particle duality. In this theory, every physical object is both a wave and a particle, and the wavelength depends on the particle mass. On this basis, photons of light were replaced by electrons with a shorter wavelength, which permit bigger magnification. During the 30s, the electron microscope family was developed using this concept and made it possible to explore the atom scale as never before. Much more recently, scanning tunneling microscope, followed by atomic force microscope, was developed by Gerd Beining, Christoph Gerber, and Kelvin Quate. 8 years later, the first AFM was put on the market, and P' Institute was among the first laboratories to be equipped. Since this day, the Université de Poitiers with P' Institute stay at the cutting-edge research in this field. In opposition to the previous microscope, the AFM doesn't use any electromagnetic wave, but a tip. The chamber analysis is composed by a tip held by the cantilever which acts as a spring. The position of the tip is monitored by a laser beam and detected by the photodiode. This signal enables to set up a feedback loop to keep the tip at the surface. Our microscope therefore scans the surface directly with the tip. In our case, the interaction measured can be attractive or repulsive forces. Indeed, the force between atoms is attractive at long distance, but it is highly repulsive at short distances. It is possible to observe a large diversity of material, both in air and liquid environment. But today's subject is biological. We want to observe the nanotexture of a snake scale. But what is the nanoscale? The magnification necessary corresponds to the size of a ladybug on a football field. When the scale from the snake is observed at low magnification, it seems to be flat. But when we get closer, some lines appear. Now, let's go deeper with the AFM. The first step is for sure to set the tip. The fragile piece of silicone is delicately attached to the cantilever to form the substrate. The sample is then strongly attached to its support, as it is important to prevent any movement or vibration of the studied specimen. Everything can be assembled in the microscope, and the laser position adjusts to point the top of the cantilever using the two top screws. As this model of microscope is also equipped with an optical microscope, we can search for a nice and flat surface. Now that we have found our region of interest, we can start to scan the sample. But be careful! This first step can be dangerous for our precious tip, which can crash on the sample. That's why we start at low magnification. After a few minutes of scanning, the results appear as a 3D map. Here, the fancy nano texture of the snake scale will help the scientist to understand the ability of the snakes to swim.